In the previous two movies in this lecture, we looked at the signals generated as a result of the primary beam interacting with the sample. We've seen that secondary electrons exit the sample, detected by a secondary electron detector, and we've seen that backscattered electrons also exit the sample, detected by the backscatter electrons. So we should realize that if we look at the image of the primary beam hitting the sample and the secondary and backscatter electrons exiting the sample, that there may be a net build-up or lack of charge in the sample. We see the situation depicted schematically on the right on the slide here. So we have the incoming electrons depicted here as a current IP, where the incoming electrons have a landing energy given by E0. Then as a result of the scattering in the sample, we have secondary electrons exiting the sample, giving rise to a current denoted here as ISE, which is proportional to the primary beam current. The proportionality factor here is denoted as delta and is the secondary electron emission yield of the sample. Equivalently, we have a backscatter electron current denoted by IBSE, also proportional to IP, with a proportionality factor here indicated with eta. And eta is then the backscatter electron emission yield. Now let's look at how these yields depend on the energy of the incoming primary electron beam. Typically, for a sample material, the yield has a curve that looks like this. On the vertical axis, we see the sum of delta and epsilon, so the total yield of electrons exiting the sample. If this yield is higher than 1, there's more electrons exiting the sample that are entering the sample, so we have a buildup of positive charge in the sample. If this yield is lower than 1, we have more electrons entering the sample than there are exiting the sample, so we have a net buildup of negative charge. Now we should realize that if a sample is conductive, this is not a problem, because there will be a current through the sample to ground, which compensates for this charge buildup. Also, if the sample is insulating but covered by a conductor, we will have this charge buildup, but the covering conductive layer will work as a Faraday cage, shielding the incoming primary beam from the effect of the charge buildup below. However, if this is not the case, this charge buildup may lead to a deviation of the electron beam resulting from the electron field generated by the buildup charge. Now let's look in a bit more detail at this curve. On the horizontal axis, we see the energy of the primary electrons, EP, and I've indicated two positions for a specific landing energy E0, situation A and a situation B. We also see that if we look at the yield curve, that there are typically two positions at which the yield curve crosses the value of 1, denoted here by E1 and E2. So these are the points where even an insulating surface will not show charge buildup. However, if we have an incoming primary electron energy E0 in between E1 and E2, like the situation A indicated here, we will have a buildup of positive charge, so a positively charged sample after a short period of irradiation. Now, if the sample charges positively, this means that the incoming electron beam is accelerated, so the incoming primary landing energy shifts to slightly higher values. And also it means that the secondary electrons ejected from the sample are attracted back to the sample, so actually the secondary electron emission yield lowers a bit. This means that we move from the landing energy E0 to a slightly higher landing energy, where the attractive action of the positive charge buildup has so much lowered the secondary electron yield that the total yield becomes 1. This is indicated by the small green arrow. Now let's look at the other situation, where we have a primary electron landing energy larger than E2, indicated by the point B. So in this case, we see that the total electron yield is lower than 1, so the system would show a buildup of negative charge. Now, negative charge means an electric field that decelerates the incoming primary electron beam and may also deviate the beam from its initial trajectory. But most importantly, the deceleration will cause the landing energy to decrease. So we see that we move E0 to lower values where the total electron yield would go up. So we gradually move up the curve, and we would reach an equilibrium stationary situation when the yield would again approach a factor of 1. However, we should also realize that the charge buildup may be so high that the total electron beam may be reflected and that the signal we detect actually originates from the objects inside the electron microscope. And in fact, if you have a sample which shows considerable charging, you may reach a condition where this reflection is such that if you scan the beam over the sample, you actually generate a reflective image of the interior of the scanning electron microscopy chamber. We should now realize that in the situation B, we have two different effects playing a role in reaching the stationary situation. First of all, by lowering the primary electron beam, we increase the yield so that we approach the situation, the point E2, where the total yield is 1. Also, if the charge buildup is considerably, we will reflect the incoming primary beam, bringing the system back to a stable situation by allowing the charge to time for the charge to dissipate from the sample. Now, on the next slide, you see a typical illustration of a charging artifact. This is a conductive sample with a piece of dust on top. You see the piece of dust appear very, very brightly due to the secondary electron contrast, and you see dark streaks surrounding it. So these dark streaks come from the charge on the insulating sample and the counter charge in the conducting surface below. You see that depicted on the image to the right. The electric field lines that originate from these positive and negative charges deflect both the incoming primary electron beam and also the secondary electrons generated in the underlying substrate, leading to the occurrence of the dark lines. Note that the dark lines occur in the direction of scanning. Note also that this is a situation of negative charging, thus a situation where we have an incoming primary electron energy larger than the E2 that we saw in the previous graph. Now on this slide you see an example of polymeric beads, so insulating beads on a conductive substrate recorded at various different landing energies, going from 6 kilo electron volt on the upper left to 0.6 kilo electron volt in the lower part. Now the electron energy in this range goes from a situation where actually most of the primary electrons penetrate through the beads into the underlying conductive substrate, which would also lead to a mitigation of charging effects in the image, to a situation where we cross E2 and we would observe positive charging. Now the question that concludes this movie is which of these images show negative and or positive charging artifacts? You can answer this question on Brightspace now that this movie is over.